Okay, so tomorrow I'm going to be reviewing chapters 1 through 5 and give a comprehensive overview of everything we've done so far. Chap, we're on chapter 7 today on steady state error. We'll probably finish this on Monday, if not today. And then we can start on chapter 8, which is going to be where things get where I think there's more controller design on chapter 8 and 9, and then chapter 10 is going to be frequency stuff. Midterm on Monday. I'll make a formal announcement tomorrow about details on Monday, and also for the online students as well who will be taking it online. All right, so let's get started. Yesterday we were deriving, or yesterday we started on steady state error. Basically, steady state error is going to be can be zero, constant, or increasing. And depending on your system type, you can determine if it's going to be zero, constant, or increasing. And you also apply these inputs, these test inputs, and they're all unit sized. So they all have a size of 1. And then we talked about sources of steady state error, or at least one source. And then today we're going to be talking about, we're going to continue off of that. So let's do a simple derivation on a system with a low system order. And one thing I want to define, but I don't have in the notes, I'll probably add it in the future, is that there's going to be something called a system type. And I've only seen this used in the textbook. And what it means is if I have specifically a open loop transfer function corresponding with this feedback diagram. And this is based on your open loop transfer function. And basically what we're looking at is we're looking at the denominator terms. And if I'm able to pull out a pole at the origin, that's going to be my system type. Where system type, maybe I'll write this in green. Is type n. So if n is equal to 1, you have a type 1 system. If n is equal to 2, you have a type 2 system. If n is equal to 0, meaning you have no poles at the origin, you have a type 0 system. There's going to be a table at somewhere in this lecture slides that will tell you, based off of your system type, if you're going to have a constant, 0, or growing error at steady state. Okay, so for this derivation, what I'm going to do is I'm going to derive I'm going to derive the error for type 0 system. So I'm going to be deriving the steady state error for a type 0 system. For a step input. And if anything, what I'm trying to conclude with this derivation is to prove that steady state error is always non-zero for a step input on a type 0 system. So type 0 meaning n is equal to 0. So that's the goal of this derivation here. I want to show to you that for a constant input, we will always have steady state error for type 0 system. So a system with no poles at the origin. So the idea behind that, so to start that proof, first we gotta look at error, which is going to be our R of S minus G of S times H of S times C of S. Or actually, sorry, it should be C of S times H of S, where H of S is equal to 1 here. This is unity feedback as a little note. Okay, so for step input, actually, regarding this statement, what we're trying to prove is this. E of S is equal to R of S minus C of S. And when we take the inverse Laplace transform of this, we're basically trying to prove that E of t, which is equal to R of t minus C of t, is constant when t goes to infinity. Basically, E of SS is not equal to 0. So that's what we're trying to prove. And we're going to do this by proof by contradiction. Proof by contradiction. So to do that, what I'm going to say is the contradicting statement here then is saying that E of SS is equal to 0 at steady state. So another way of writing it is E at time is equal to infinity is equal to R of infinity minus C of infinity. And that's equal to 0, which implies that R of infinity is equal to C of infinity. So that's our first statement. Okay. For step input, it means that this means that R of t is equal to 1, which is non-zero for t greater than 0. Therefore, C at infinity is non-zero. Good so far? So seems like we're going in circles right now, which we are. All right. All we're saying is that for steady state equal to 0, our output C has to be equal to our input. That's all I've said so far, and that they're both non-zero. All right. Now, if we look at our output, C of S is equal to G of S multiplied by E of S because our input source is here. And here, when we look at our system, I forgot to mention, our system here is just a simple gain system, a gain of k. It's a type zero system, and it's just a gain. Then we get this term here, k times e of s. Then we take the inverse Laplace transform to find c of t. And we get k e of t. Because k is just a constant, we can pull the constant out when we do the inverse Laplace transform. All right. So then we get this relationship where we can just rearrange. We want error as expression on the left side. We get error is equal to 1 over k times c of t. So that we're saying that error is equal to 1 over k multiplied by the output. And then hopefully you can start to see where the contradiction will occur. But then, so at time is equal to infinity, we're saying that error at infinity is equal to 0. That's our contradicting statement. Then what we're saying is error at infinity is equal to 1 over k c at infinity, which is equal to 1 over k at r at infinity, because c and r are equal at steady state. But this is the contradicting statement. And I'll point out where the statements contradict. I'll use a different color here. So the first statement that's contradicting is here, where we say that, well, that's not the contradicting statement. This is true. For error to be 0, r has to be equal to c. And the fact that r is non-zero means c is non-zero. And then this is the second statement that contradicts, because since c is non-zero, we've shown that e is equal to 1 over k multiplied by c, which means that e here is non-zero. So these two contradict with the original statement. So these two statements contradicts with e of ss, or e of infinity is equal to 0. If anything, we just proven that steady state error is equal to 1 over k multiplied by our output at steady state. And the best we can do is we can only decrease error by increasing k. We can only decrease error by increasing gain. So that's an increasing gain, increasing gain. So for type 0 system, you can only have constant error, and that's for a unit step input. Any questions? Okay. So when we add a integrator, which is a pull at the origin, and if we think of s times g to be, or s times y to be the derivative, then taking y over s is the integral of y. Just a little side note. That's why we call it an integrator. So adding an integrator is going to increase the system order by 1. So this makes it a type 1 system now. This is a type 1. And notice that this is on the open loop transfer function. So then adding an integrator allows ESS to be 0. Adding an integrator allows steady state error to equal to 0 for a step input. And this is for type 1 systems, type 1 or higher systems. And this is what a PEI controller does. PI controller adds an integrator. It also adds a pole, but the point of a PI controller is to increase the system type by 1 so that your steady state goes to 0. Adding the 0 part will be something that we'll talk about in chapter 8 and 9. This is similar to a PI controller. Almost the same, but slightly different. Okay, so now we're going to derive this same thing again, where we have error here, and let's do the same thing. We assume ESS is equal to 0, which implies that our output at steady state is equal to our input at steady state, which is non-zero for step input. It's going to be constant. And we're going to just write out the output. C of S is equal to E of S multiplied by G of S. I like to write it this way instead. Which is equal to K over S times E of S. When I take the integral, or not the integral, the Laplace, inverse Laplace transform of C of S, I get C of t is equal to K times the integral from 0 to t, error at time tau d tau. So we're taking the area of the error from 0 to t. And basically, at steady state, it's going to be the limit as t goes to infinity of C of t, which is equal to the limit as t goes to infinity of K times the integral from 0 to t e tau d tau, and this is going to be constant. So adding an integrator allows our error to be constant. Well, it allows the area under the error curve to be some finite value, and this makes C of t a constant. And this is not a contradiction. Basically, what it's doing is by adding an integrator, we're just finding the area under error. So let's say we have a system with error and we're plotting it as a function of time. And error is decreasing because this is a type 1 system. We're basically computing the area under the curve. Area under error is found. So basically, this is just finding the area under the curve. Eventually, at maybe time going to infinity, this is 0. So ESS is equal to 0 for a step input on type 1 or higher systems. So in previous years, I have on a midterm given this complicated looking open loop transfer function, and I gave a step input, but the system was like a type 1 or type 2 system. And some people did calculate it and found it to be 0, but other people just said 0 because they saw that was a type 1 system. So don't jump into a problem, kind of look at it, look at the type system type, and find shortcuts of solving the problem, and you'll be able to save time. Any questions? So this kind of follows with type 2 systems. So if I have a type 1 system, error is 0 for a step input. Then for a ramp input, it's going to be constant. And then for a parabolic input, it's going to be infinite. Now, if I have a type 2 system, it's going to be 0 steady state error for a step and a ramp input and constant for a parabolic input. So it just scales linearly like that. So now we're going to move on to steady state error for unity and non-unity feedback systems. And basically, the textbook likes to use the form unity feedback systems for calculating error. Here are the equations for it. So for your open loop transfer function, G of S, and I just want to drive this point here. Open loop transfer function also includes H of S here, but for unity feedback, H of S is equal to 1. Closed loop transfer function is going to be this whole block form equivalent, which is equal to G of S over 1 plus G of S, H of S. And here, basically, this is the equation for it. Error is going to be equal to R divided by 1 plus GS, G of S. And then this is applying the final value theorem. And you can see that actually error is dependent on the poles of 1 plus G of S. Basically, what they're saying is 1 plus G, if it has stable poles, then error will also converge to either 0 or some steady state value. The way they derive that, I'll just do a quick derivation. C is equal to G times E. So output C is equal to G times E. And then E is equal to R minus C. Then you plug this back in. So then you get C is equal to G times R minus C. You separate the, oh, my bad. So should be the other way around. So E is equal to R minus C. Then you plug the C into the area equation because we're trying to get rid of C. So then we get E is equal to R minus GE. Separate the E's, and we get R over 1 plus G. That's the way you get that equation. Okay, so then Moving on, steady state error for unity feedback systems can be computed using the open loop transfer function, G of S, and the closed loop transfer function, T of S. So if we have the closed loop transfer function form, this is the equation for it. A little bit different, but if you usually it's easier to use the open loop transfer function. This is usually open loop transfer function is easier to find. But using closed loop transfer function is perfectly valid. The reason why open loop transfer function is easier to find is usually you're given a plant and they have a feedback. If you do the feedback, you have to just do a little bit of arithmetic to find a closed loop transfer function. So it's just an extra step. Okay, well, what happens when you have non-unity feedback systems? Well, we can actually just use the same exact equations from earlier and just derive we can derive the error, but instead the textbook has a little bit of a convoluted way of finding it. I don't know why they just couldn't have a second set of equations in terms of h, but instead this is what they did instead. So what they're doing is they're going to have g and they have an h here. And block diagrams returns in this derivation. And then on top of that, they basically add, I'm gonna make a little space because I'm gonna be adding 4 signals to this summing junction. And there you go. So we have that block, and actually I'm gonna put a -1 here. So we're taking this signal and multiplying it by -1. And then we're gonna add one more block line here. So this top block and this bottom block are the equivalent blocks because these two lines I added are signals that cancel each other out. And then what the textbook does is they then add these two lines together using the parallel rule. So once you get that, you get this block diagram. And I'm gonna draw 2 more. So I'm gonna draw one on the left side here. So you get that. Do note the signs at the summing junctions. Since all of these are negative, we can add the h and -1 because the negative is still being applied at the summing junction. Then here we're going to apply feedback rule on the inner block. Apply feedback rule. And maybe to Perhaps to make this visual a little easier, I could redraw the block diagram like this. They're the same thing. What I just erased and redrew is the same as what I just drew now, but maybe this is a better visual of why we can do what we did. So they all share the same feedback line, and the summing junctions can be split up with a redundant line in the middle here. This is redundant. We don't need it. But this is just good for visualization. So once we apply the feedback rule, we get this final form. Do I have the equation? Oh, I do have more space. All right, well, we get this final form. Maybe next time I'll just put it all on one page. We get G over 1 plus G times H minus 1. With feedback. With a negative unity feedback. So this is similar to your homework 1, where I told you to simplify your block diagram into equivalent G and equivalent H. And this is one of those tricks where you can move the H back into the G block and have H equal to 1 as well. So now that we have this basically called G equivalent, we now have H equivalent equal to 1, and then we can now apply it to the equations from the previous page. So this is the final expression for it, and that's the goal. So now we can just apply it to one set of standard equations. And here's this chart that I think is useful for finding steady state error. Basically, when you have a step input, this is how you find the steady state error of your a system with unity feedback or equivalent unity feedback. And a ramp input, note that the 1 plus GS, but here it's just S times GS, and here it's S squared times GS, G of S. That is intentional. And then here they define KP, KV, and KA. They're just basically constants. It's just to make this table a little shorter. So you can see for step input, it's going to be 1 over 1 plus KP. For steady state error for ramp, it's 1 over KV. And for parabolic, it's going to be 1 over KA. I need to capitalize these Ks. We have a question online.
Yeah, so can you hear me? Hello?
Let's see. I don't hear you, but I think that might be on my end. Hold on a sec. Am I speaking again, Xander?
Hello? Hello?
Yeah, I hear you, but
Okay, that's great. Yeah, so my question is, can you explain how we know that G subscript EQ equals 1?
it's not equal to 1. It's H equivalent is equal to 1. Yeah, that's probably put this on a different line.
Oh, I see. Okay.
Yeah. This block here is G equivalent.
Okay, got it. Yeah, I thought you were saying that G equivalent equals H equivalent equals 1. But I see,
Oh,
I see.
no, that's confusing the way I wrote it. That's a better way of writing it out.
Cool.
Yeah, so
Thank you.
that way when we get that, we can apply it to this equation here again. All right. So there's that. Now let's look at an example. Basically, we want to find the value of K such that the steady state error is only 10% for a negative unity feedback system. So unity meaning H of S is equal to 1. And then note that this is a type 0 system, meaning that there is going to be steady state error for a step input specifically. Sometimes I might leave that information out because you have to kind of deduce um, from the information given. So ESS is constant for a step input. And if we want 10% error, let's just use a unit step input. So that means, yeah, question. Oh, yeah, because it's a no number of poles at the origin is going to be your system type. So 0 poles at the origin is type 0. Number of poles at the origin is your system type. Maybe I should write that more formally. I'll move that to the other page as well. And when I say poles, it's going to be your open loop poles, not your closed loop poles. Because once you close the loop here, your poles at the origin will no longer be at the origin. Yeah, no problem. I may, sorry, real quick, put this on the other page. I really need to define, I'll update my notes. Maybe if I'm still here next year. I hope I'm gone by next year, but probably not. Anyway, I'll put it right here. I need to add that as a all right. So we have a type 0 input or a type 0 system. So based off of that information, it's only going to be constant for step input. And this is only true as well if the system is stable. System is going to be stable. Uh, yeah. So anyway, we want error at steady state is equal to 0.1. Then this is going to be for a unit step input because it's going to correlate with 10%. Let's say error at steady state is equal to 0.2, then this is going to be for an input of 2. For a input R of t is equal to 2. Makes sense? It just scales linearly with your input size. So it just depends on your input size. So we're going to stick with unit step input, then it makes everything easy to read. So then we know from the previous table, error at steady state is equal to 1 over 1 plus Kp, where Kp is equal to the limit as S goes to 0 of G of S. So then let's just solve for that. Limit as S goes to 0 of small k multiplied by S plus 10 divided by S plus 14 times S plus 18. It's going to be equal to 5k over 126 when we multiply that all out. Then we just get E of SS is equal to 0.1, which is equal to 1 over 1 plus 5k over 126. And then we get k is equal to 226.8 for that to happen. So pretty large gain, but that's the price you pay for reducing steady state error. So one thing about this equation here is that this equation is only for unit step inputs. Because E of S is equal to R of S divided by 1 plus G of S. So the reason why I say if you have a different size input, then R of S is also going to increase in size. So the way they found E of S is by applying the final value theorem, where error at infinity is equal to the limit as time goes to 0 of S times E of S, or not time, S goes to 0. And that's going to be equal to S times R of S divided by 1 plus G of S. So this is the general universal, this is the, I guess, the universal equation for finding steady state error for a non-unity or for a non-zero, no, for a non-unity input. And it'll also work for unity input as well. I don't think the textbook has this equation. General E of SS equation. So the textbook likes to take that shortcut. So the reason why this works is because for a, let's say for R of S is equal to 2 over S, this is going to be for the input of 2 now. We get this. The S's cancel out and we just get E at infinity is going to be equal to limit as S goes to 0 of 2 over 1 plus G of S. So it scales linearly with the input. Any questions?
Sorry, I have another question.
Yeah.
Is this for an open loop system?
Yeah, so no, this is going to be for a closed loop system. This is the error of the closed loop system. So this is error for the closed loop system, but we're using the open loop transfer function to calculate the error.
Okay, that's why HFS isn't there. Okay, thank you.
Yeah, no problem. So using open loop transfer function to find error of the closed loop transfer function. So that's actually another good point to make. That was a great point. Yeah, question. Oh, this should, yeah, that's not 5. Yeah. Don't make that mistake on the midterm. 2 over S. It's just like, yeah, there you go. It's not 2 over 5. Man, that's a pretty bad S. I could use cursive S. Anyone remember cursive? Yeah. Yeah. What the hell is that? Yeah. Yeah. Okay. So next we're going to talk about steady state error for disturbances. So now if you have a disturbance, you're going to enter your system. So this is an example of a disturbance source. This is specifically from the textbook, but it can pop up some elsewhere. It can also pop up, like perhaps we can have the disturbance pop up here instead. So maybe we have our controller and plant. So I'm going to combine the controller. Well, actually, no. I have the controller. I have my plant. And we can have disturbance appear here. And sometimes the way we like, maybe the disturbance is actually not external. Maybe it's modeling error from the plant, but we just put it there saying that the plant is affecting the output reading. So we have disturbance there. That's another source of disturbance. Here, this could be controller disturbance, or there could be something that is also affecting the reading from the controller going to the plant. Maybe it's not the controller disturbance. Maybe wiring's bad, causing maybe there's noise leaving the controller. We can also have disturbance appear in the feedback sensor. So this is disturbance occurring at the feedback. The point I'm trying to bring up here is that this isn't the only source of disturbance, or it can pop up anywhere. So depending on how it appears in our system, we can draw our body diag or our block diagrams accordingly to most accurately determine the source of the disturbance, and then we derive the output based off of the disturbance source. So today's, or I guess on Monday, I'll derive the disturbance. I'll derive the output as a function of the disturbance and as a function of the input. So maybe like to visualize it, input signal goes through and goes back to the feedback. And then the disturbance is going to go through the plant and then go through the feedback and pop up as the output. And this is just more of an analysis tool. The equation provided in this derivation isn't a set rule of disturbance is from here. Disturbance can pop up anywhere. So we'll talk about that on Monday. Tomorrow, if you want to come in for the review session, you're more than welcome to. If you feel confident for the midterm, you can skip it. And I'll see you all tomorrow.